In this second part of the lesson, we introduce the TS diagram and we make some more applications to understand the concept of irreversible transformations. The TS diagram is very powerful to calculate the heat and work of a cycle. Let's consider a cycle made of three transformations, very general and reversible, and the mass of 1 kilogram. The Q is the sum of the Q of the transformation AB plus the Q of the transformation BC plus the Q of the transformation CA. And this we can express as integral from A to B of TdS and the same for BC and for CA. Altogether, this is a cyclic transformation and we can recognize that it corresponds to the area ABC. We remember that the thermodynamic work is Q minus delta U, but for a cycle, delta U is 0, also it remains only Q. L and Q are equal. In this diagram, it's definitely possible to calculate Q directly as integral, as we have done for the thermodynamic work using the diagram PV. For a transformation, the thermodynamic work is calculated by difference between Q and delta U. If Q is positive, also the work is positive, the cycle is traveled clockwise, same rule as per PV diagram. If the transformation is irreversible, then Q cannot be calculated like that, also cannot be calculated by using the integral form of T into ds. The isothermal transformations are horizontal segments, and those are also isenthalpic and isodynamic for a perfect gas, while the adiabatic transformations, if reversible, are vertical segments. Let's see a Carnot cycle in the TS diagram, and we consider, always for a perfect gas and unitary mass, the same transformation references used in the PV diagram at slide number 6 in the previous presentation. Transformation 1 is the isothermal AB, transformation 2 adiabatic BC, transformation 3 isothermal CD, transformation 4 adiabatic dA. And we'll calculate now the heat of every transformation and then the work. The Q over the transformation AB is the TA into the difference of the entropy of the point B and A. And because this difference is negative, the Q is negative. The Q along the transformation BC is 0 because adiabatic. The Q over the transformation CD has a similar expression as the Q of AB because isothermal, but in this case is positive. And the Q over the transformation dA is still 0 because adiabatic. The thermodynamic work is the sum of the heats of all the transformations, but since we have only two non-zero transformations, we consider only the QAB and QCD, and it is given by this expression. We can recognize this is the area of the cycle ABCD. What is the efficiency of the cycle? The efficiency, for definition, is the ratio between the thermodynamic work and the sum of the positive heat. But the positive heat is only the heat over the transformation CD. We write the expression of the work at the numerator, the expression we have found in the previous slide, and the expression of the heat at the denominator. Eventually, we recognize that those cancels out and remains only the expression already calculated by the PV diagram at slide number 7. What happens if the cycle is irreversible? Let's see some example. The first example is when the transformation dA, this transformation is irreversible. but still adiabatic. In this case, the entropy of the point A' is greater than the entropy at the point A, but the temperature stays the same and keeps equal to the temperature of point B. The heat over the transformation A'B is the temperature at point B, that is the same as the temperature at the point A', into the difference of the entropy between point B and point A'. And we recognize that this heat is negative. The heat over the transformation dA' is zero because it's adiabatic, regardless if reversible or not. The new work L' is the sum of the heats, and we can express in the form written in blue. We recognize this expression is not the area A, B, C, D, and neither the area of the cycle. The new efficiency is the ratio between the new work and the given heat that in this case does not change. And we find this expression where the contribution of the ratio SA' minus SB over SD minus SC is greater than unity. Therefore, this efficiency is less than the efficiency of the reversible cycle. We notice that the total delta S increases. In fact, the total delta S is the sum of the delta S of the system and the delta S of the surroundings or the delta S of the recipient. But the delta S of the cycle is 0. Also, negative Q over the transformation CD over the temperature in C, because the temperature is constant, minus the heat over the transformation A'B over the temperature in B, equals negative entropy in D minus entropy in C plus the difference of the entropies of the points A'B. And this is positive, confirming the Clausius statement of the second thermodynamic principle. Let's consider now another case when the transformation C'D' is irreversible, isothermal transformation. The temperature in C' is less than in C, and the temperature in D' is less than in D, and thus new temperatures are equal because the transformation is isothermal. The entropies does not change with respect to the reversible case. The heat over transformation AB has the same expression as already seen in the reversible case. The heat over transformation C'D' is the temperature in C' into the differential entropy, which has not changed, and this is positive. The new work is the sum of the heats over the transformations C'D' and AB and assumes the form in blue. We recognize this is actually the area of the new rectangle ABC'D', but this area is less than ABCD of the rectangle in the reversible case. The efficiency is also the ratio between the work and the given heat. The given heat is only the heat exchanged over the transformation C'D', and we find this expression 1 minus Ta over Tc', and because the temperature in C' is less than the temperature in C, this efficiency is less than the efficiency of the reversible case. Let's introduce now a new argument, that is the Carnot factor. Thanks to the Carnot efficiency, we can study the behavior of a more complex cycle under changed conditions. The Carnot factor is so defined, is the ratio between the efficiency of the cycle and the efficiency of the Carnot cycle, okay? And this is of course depending upon the minimum and maximum temperature of the cycle. We can assume that the Carnot factor does not change if the temperature changes slightly. We can calculate the efficiency of the cycle under changed conditions. For instance, for a higher maximum temperature, we call here T3, as the efficiency of the Carnot cycle under changed conditions into the Carnot factor, assuming this is not changing, as told before. This is an approximation, but it works quite well in most of the practical applications. Let's do an example in the diagram PV as seen at slide number 4 for a perfect gas and a unitary mass. We write here in the table the corresponding values of the states of the cycle. The state A has pressure 100 kilopascal and 1 cubic meter per kilogram as a volume, and the temperature is 75.2 degrees. And for the remaining states are also the given values. The maximum temperature we find for the point C, 1120.3 degrees. R is 287.1, CV 717 and CP 1004.1 joule over kilogram per Kelvin. This is for the perfect gas air. As seen in the slide number 5, the efficiency has this expression. If we replace the values that we find in the table, we come to the efficiency of 10.5%. Question: what happens if we change the maximum temperature of the cycle from 1120.3 to 1500 degrees? To calculate the efficiency, we simply replace the new values that we find in correspondence to the new states C' and D', and we find an efficiency of 11.6%. But we could come to an approximated result using the Carnot factor, and this will be quicker, especially if we could not know the formula of the efficiency. Okay, this is just for example. Also, we calculate first the Carnot efficiency of the original cycle, when the minimum and maximum temperature are the one displayed here. For the state A, 75.2, and for the state C, 1120.3. And we come to an efficiency of the Carnot cycle of 75%. Then we calculate the efficiency of the changed cycle, which is the one when the maximum temperature is 1500, and we come to an efficiency of 80.3%. The Carnot factor is the ratio between the efficiency of the cycle, calculated above, 10.5%, and the corresponding Carnot efficiency, 75%, 0.14. Now we can say that the efficiency of the cycle under changed conditions, also with the maximum temperature of 1500 degrees, is the product of the Carnot efficiency of the changed cycle and the Carnot factor, assuming that this is not changing this value. And we come to an efficiency of 11.3%, which is not far from the one we calculated exactly. The approximated result works well the higher is the efficiency. For very low efficiencies is not very precise, but it gives an idea. Everything that we have discussed till now about the efficiency can be only applied to the generating machines, also machines converting heat into work. What happens for machines converting work into heat? Those cycles are traveled counterclockwise as displayed in the picture. We can define two quantities. The first definition is the coefficient of performance, that is, the ratio between the sum of the heats Qi prime, where Qi prime is the heat released to the ambient, and the thermodynamic work, and this quantity is greater than 1. Since Qi prime is the heat released to the ambient, it is negative for definition, as well as the thermodynamic work because it is given to the system. So at the end, this quantity is positive. Energy efficiency ratio is the ratio between the negative sum of Qi star over thermodynamic work, or we can express as positive sum of Qi star over technical work, remembering that thermodynamic and technical work are opposite in a cycle, and also this quantity is greater than 1. Qi star is the heat given to the system, being Qi star positive for definition. Definition 31 is used for heat pumps, while definition 32 is used for chillers. For a Carnot cycle, like displayed in the picture, we can express COP as QCD over thermodynamic work, and the work we can express as the sum of QCD and QAB. And since those are isothermal transformations, we can express Q as T into delta S, and eliminating delta S, we find this simple expression, TD over TD minus TA. This is a positive quantity and also greater than 1. In the same way, we can express the EER as negative QAB over thermodynamic work. And we find this expression also very simple, TA over TD minus TA, that is also positive and greater than 1. We remember those are only valid for the Carnot cycles. Now we see what happens if the cycle is irreversible. For instance, if the transformation BC' is adiabatic irreversible. In this case, the entropy of the point C' is greater than the entropy of the original point C, because the point is moved to the right side. The COP' is the heat of the transformation C'D over the thermodynamic work in the new condition. And this work we can express as the sum of QC'd and QAB. Replacing the expression of the heat for the isothermal work, we find this relation. And if we call epsilon the difference of the entropy of the point C' and the point C, and we call delta S the difference of the entropy of point B and A, which is the same as between points C and D, we can express it as the ratio between the product of TD and delta S plus epsilon and TD into delta S plus epsilon minus TA into delta S. And the inverse of COP' is 1 minus TA over TD into delta S over delta S plus epsilon. And because this quantity is greater than 1, then 1 over COP' is greater than 1 over COP. Therefore, COP' is less than COP. In a consistent way, we can demonstrate that EER of the new cycle is negative QAB over the new work, but QAB has not changed, just the work. We replaced the expression already found for the work, and using the same parameters delta S and epsilon already seen, we come to the conclusion that the inverse of EER prime is greater than the inverse of EER, because this quantity is greater than 1, and therefore EER prime is less than EER. We can find similar results if we consider other transformations irreversible. As a general message, the irreversible transformations are worsening the performance, and this is not only valid for the generating machines, but also for the operating ones. Let's conclude this lesson with some considerations about irreversible and reversible transformations. A transformation is irreversible when it is valid, the Clausius statement of the second thermodynamic principle. The difference of the entropies of the states A and B is greater than the integral between the same states of dq over the temperature of the surroundings. For any transformation where dq is different than zero, either positive or negative, we can calculate delta S using a corresponding reversible transformation between the two known states, because entropy is a state function, and for that we can use any of the formulas seen at slide number 12. This concept is very important. If the temperature of the surrounding is constant, we can calculate delta S of the recipient as the negative ratio between the exchanged heat and the temperature of the surroundings. If the transformation is irreversible, then the temperature of the surroundings or the temperature of the recipient is greater than the temperature of the system. When heat is positive, the system receives heat, or vice versa. For an adiabatic transformation, Q is 0, delta S of the surroundings is 0, and the delta S of the system can be calculated with the formulas seen at slide number 12 for the irreversible transformations, otherwise it is 0. For an adiabatic transformation, reversible is delta S 0, and from the formula 26 we can express this delta S in this form: Cv into logarithm of P2 over P1 plus Cp into logarithm of V2 over V1, and this is equal to 0 for definition of reversible transformation. Therefore, if we divide by Cv, we can write logarithm of P2 over P1 plus K into logarithm of V2 over V1, being K the ratio between Cp and Cv. Also, logarithm of P2 over P1 into V2 over V1 to the power K equals 0. And then P2 over P1 into V2 over V1 to the power K is equal to 1. And then P2 into V2 to the power K equals P1 into V1 to the power K. That demonstrates the formula number 33, well known, of the isentropic transformations. P into V to the power K is constant. In the last slide, as usual, we resume all the formulas used in the lesson number 3, so including also the ones displayed in the previous video. Those formulas are useful for being recalled in the next presentations. Thanks for attending. See you next time. Bye bye.